Ever stop to think, like when you're going about your day, that all the stuff around us, our phones, even this coffee, it's all like following a set of rules.
It's true.
Not social rules or anything. I'm talking about the actual laws of physics, the stuff that makes reality, well, reality.
It's a pretty mind-blowing thought when you actually stop to consider it.
Right. So what we're diving into today is whether those rules, that like code of the universe,
hmm
is actually something we've pretty much figured out.
Exactly. At least when it comes to a certain zone of reality, the stuff we experience every day.
Okay, so before we get too far, we should probably say up front, we're not claiming physicists have the entire universe solved.
Definitely not. Dark matter, what happened right at the Big Bang,
Mm.
those are still mysteries.
But there's this idea, and it's a big one, that for the world of, atoms and the particles that make them up, we have a really, really good model.
Yeah, shockingly good, actually.
And that model is what some physicists are calling the core theory. So where do we even begin unpacking something that big?
Well, a good place to start is with this thing called effective field theory. EFT for short.
Catchy.
Right. It might sound kind of intimidating, but it's actually a really elegant way of looking at things. Imagine like a photograph, right? You see the whole picture, but zoom in close and you get the individual pixels.
Got it.
EFT is kind of similar, but instead of pixels, we're talking fundamental particles. Quarks, electrons, that level. EFT is basically a set of equations that describe how all those particles interact to create, well, everything.
So we're talking about the most basic building blocks of matter here.
Exactly. And the crazy thing is, EFT doesn't just describe what we already know. It can actually predict how particles should behave in situations we haven't even tested directly.
That's wild. Okay, so we've zoomed in from the everyday world to this subatomic level, to the realm of these fundamental particles. But what is this core theory actually made of? What's in it?
At its heart, you've got the standard model of particle physics. If you've ever wondered how forces work, like not just gravity, but the stuff holding atoms together, the standard model is where you find the answers.
So that's where we get electrons and protons and all that, right? Like the basic stuff of chemistry class, but way more intense.
Yeah, exactly. But instead of just saying protons exist, the standard model tells you what they're made of, quarks, how they interact. It even predicted particles we didn't discover until recently, like the Higgs boson.
Right, the Higgs. That was huge news. So this standard model, it covers most of the forces we know about, but what about gravity? Like the force that keeps us from floating off into space? That's kind of important in our everyday lives.
Totally. And the core theory does include gravity. But here's the thing. It uses a version of Einstein's theory of general relativity, specifically something called the weak field limit.
Weak field limit sounds a little niche, to be honest.
I know, right? But don't let the name fool you. For pretty much everything we experience, planets orbiting, apples falling, all of it, this version of Einstein's theory works incredibly well. It's just that when you get to really extreme situations, like black holes, that's when you need the full, mind-bending version of general relativity.
Okay, so it's like we've got the everyday gravity guidebook, which is super accurate for most things, and then there's the advanced black hole edition.
Exactly. And it turns out that everyday guidebook, along with the standard model, seems to be doing a fantastic job of explaining the universe as we know it.
Which leads to a pretty big question. How can we be sure there aren't other particles or forces out there, stuff we hasn't discovered yet, that might be messing with our understanding of reality? Like, what if there's more to the story?
Now that is the million-dollar question, and it's what keeps physicists up at night. Or,
Yeah.
well, in the lab, more likely. It's kind of like, well, you know how in physics there are always these big discoveries that change everything?
Yeah.
Take neutrinos, for example. For the longest time, they were just theoretical, like they should exist, but we couldn't actually detect them. Turned out they were just super, super good at hiding.
Hiding? You mean they're like sneaky particles?
Kind of. They're incredibly light, almost massless, and they barely interact with other matter. Like trillions of them are passing through you right now, and you'd never even know it.
Whoa. So they're like tiny little ghosts just zipping through the universe.
Exactly. But here's the thing. Even though neutrinos are everywhere, they don't really do anything to us. Their effect on our everyday reality is basically zero.
So for a new particle to really rock our understanding of the universe, it couldn't be like a neutrino, right? It'd have to be Stickier.
Exactly. It would have to interact with other particles way more strongly, enough to actually make a difference that we could observe. And trust me, physicists are really good at observing
So
things.
you're saying our experiments are sensitive enough to pick up even the faintest whispers of new particles? Like we'd have found them by now if they were out there.
We've got some pretty incredible detectors out there, looking for any sign of something out of the ordinary. So far, nothing quite as dramatic as a whole new particle.
Okay, so maybe it's not about new particles, but new forces. We've got the four fundamental forces, gravity, electromagnetism, and the two nuclear forces. What if there's a fifth one lurking out there that we just haven't detected yet?
Another great question. And yeah, physicists are definitely looking into that. But it gets tricky because, unlike particles, which we can sometimes see directly, forces are a bit sneakier. You have to infer their presence from how they affect other things.
Give me an example.
Well, take gravity. We experience it all the time, right? It was what keeps our feet on the ground. But the theoretical particles that actually carry gravity, gravitons, we've never actually observed one directly.
So how do you even go about looking for a force if you can't see the thing that's carrying it?
You look for its effects. You see how it influences the world around it. Physicists have come up with some really clever ways to do this, and one of the tricks is to look at how the strength of a force changes with distance.
Okay, I'm following so far.
Imagine you've got two magnets, right? Hold them close together, and they pull towards each other really strongly, but move them farther apart, and that force drops off really quickly.
Yeah, I get that.
Different forces have different fall-off rates. It's like their fingerprint, how their strength changes over distance. So by looking at how forces behave at different scales, physicists can actually tell if there's something extra going on, a force we haven't accounted for.
So it's kind of like tuning a radio, trying to find a signal amongst all the static. But in this case, the signals are the forces themselves.
Exactly. And so far, at least in the everyday world, the scales of our lives, our planet, even our solar system, the radio dial of physics, seems pretty quiet. No sign of a mysterious fifth force messing things up.
So you're saying if there is a fifth force out there, it's got to be incredibly weak.
It would have to be weaker than gravity, even, which is saying something because gravity is already the weakest of the four known forces. But even though it's weak, it still holds entire galaxies together. It's pretty wild when you think about it.
So we've got these incredibly powerful forces holding atoms together, and then this other force, gravity, that's super weak but acts over these vast distances. It's almost like two different sets of rules for two different worlds.
It is kind of like that, yeah.
Yeah.
And yet both of those worlds, the tiny world of atoms and the vast world of galaxies, are ultimately governed by this same core theory. And that leads us to some really, really interesting implications. Because if this core theory is as complete as it seems, at least for our everyday reality, then it kind of throws a wrench into a lot of ideas that people speculate about, things like ESP, or the idea that there's a soul that exists beyond the physical body.
So you're saying because we have this really good understanding of how the universe works, those other ideas become harder to justify from a scientific standpoint.
It's not that science is trying to disprove them exactly. It's more like if ESP is real, or if there is some kind of soul separate from our bodies, then it would have to work in a way that doesn't contradict the fundamental laws of physics that we already understand pretty well.
So it's not impossible, but the bar for evidence just got a whole lot higher.
Exactly. And that's kind of the amazing thing about science. The more we learn, the more we realize how much we don't know.
Yeah.
But even if the universe is a little less mysterious, now that we have this core theory, I'd argue it's actually way more incredible because we can start to appreciate just how much complexity can arise from a few basic rules.
So we've gone from puppies to particles, but it feels like we're left with a pretty big question.
Shoot, what's that?
If we understand the basic code of the universe so well, at least in our everyday experience, how do we get all this complexity?
Yeah.
Life, consciousness, just the sheer variety of stuff in the universe. I mean, that's not all directly written into the laws of physics. Right?
You're hitting on one of the most mind-blowing things about it all, actually. It's what we call emergence, this idea that from just a handful of simple rules, you can get incredibly complex systems. Think about it like, well, you know the rules of chess, right? You know how each piece moves, all the legal moves, but that doesn't mean you can predict every single move a grandmaster is going to make, right?
No way.
Exactly. The complexity comes from how all those simple rules interact over time, all the different possibilities.
So even if the core theory gives us the fundamental building blocks, the really interesting stuff is how those blocks come together over time.
Exactly. And it's not just theoretical. Like, think about us right now having this conversation. The fact that we exist, that we're able to do this, it's a testament to the power of emergence.
It's kind of mind-boggling when you put it like that.
Trillions of atoms, all following the same basic rules of physics, and somehow you get a living organism. Cells, organs, and eventually consciousness. Even our most powerful computers struggle to simulate anything close to that.
It really makes you appreciate just how interconnected everything is, right? Like from the smallest particles to the biggest structures in the universe, it's all running on the same fundamental operating system in a way.
It really is humbling. And it makes you wonder, if this level of complexity can emerge from what we currently understand,
Yeah.
what else is possible? What else might be out there within the framework of the core theory that we haven't even begun to imagine?
That's a pretty exciting thought, honestly.
Right.
So it's kind of a paradox. We've talked about how the laws governing our everyday reality might be surprisingly well understood, thanks to this whole core theory thing, the standard model, the weak field gravity guidebook.
Yeah.
But then at the same time, there are these huge mysteries about how those rules actually play out in the grand scheme of things.
It's like we've been handed this amazing toolkit. We know how to use the tools, but the really groundbreaking inventions are still waiting to be built.
And we've only just started exploring what's possible.
That's what's so exciting. And it makes you think, if we've been able to learn so much from studying the universe from the outside, what could we discover by turning that same curiosity inward?
Towards, you mean like understanding our own consciousness?
Exactly. If physics can tell us about the origin of the universe, maybe it can also tell us something about the origin of our own minds.
Mm-hmm.
But that's probably a deep dive for another day.
Definitely. For now, it looks like we've reached the end of our journey from puppies to particles. We've explored this idea that the laws of physics, at least the ones governing our everyday lives, might be surprisingly well understood.
And we've seen how physicists are really pushing the limits, searching for new particles, new forces, anything that might shake up our understanding.
And we've only just scratched the surface of this idea of emergence, how simple rules can create incredible complexity, from the birth of stars to, well, us.
So, yeah, we may not have all the answers, but hey, that's part of the fun, right?
Absolutely. The more we discover about the universe, the more we realize just how much more there is to learn, which is a pretty amazing place to end, if you ask me.
Totally.
To all our listeners out there, thanks for joining us on this deep dive. We hope it sparked your curiosity and, hey, maybe even inspired you to ask a few big questions of your own. Until next time.